Welcome to this presentation called What Goes Inside an iPhone. It was divided into 5 blocks called Energy and Mainboard, which is today's subject, Access, which deals with the main ways of interfacing with a smartphone, radios and antennas, movement and location, so most sensors are here, and finally cameras. There is also an important introductory video which establishes a common ground. If you haven't watched it, I suggest that you do before you proceed. Let me show you all the videos together. Here they are. Access was split into 2 videos because the subject of display, which includes also the touch screen, is longer than the others. Today's subject, energy and mainboard. So we start with the battery. Here are 3 examples from iPhone 11, 10, and 11 Pro. This is rectangular. These 2 are L-shaped with higher capacity, but this one wasn't well integrated yet. Today's material is lithium ions. So this is the material that goes through the electrolyte from the negative to the positive electrode during discharge and back during recharge. It has high electric density, low weight, low self-discharge, and very important, no memory effect. So the battery can be charged as many times as we want and as much as we want. 2 examples of major manufacturers are listed here. Some questions about typical parameters for smartphones in general. So let's check our answers. Voltage 3.8 volts, current capacity between 3 and 4 ampere hour, and multiplying the 2 you get the total capacity between 11 and 15 watt hour, and the weight is typically under 150 grams. Just for fun, another set of questions to compare the smartphone battery to the battery of this motorcycle. Let's see if the smartphone battery can run this motorcycle. Voltage 12 volts, current capacity 4 to 5 ampere hour, total capacity multiplying the 248 to 60 watt hour, weight around 2 kilograms. So no, this battery cannot run the motorcycle yet, but it's already 1/4 of it. And the weight is much smaller than 1/4 of the weight of the motorcycle's battery. Recharge options, there are 3. First, using a regular charger. There is a normal charger which is 5 watts and comes in the base models like the iPhone 11. And there is a fast charger which is capable of replacing 50% of the charge in at most 30 minutes. It's an 18-watt charger and comes in the top models like the iPhone 11 Pro and Pro Max. The second option is by using an USB port. USB 3.0 is capable of sourcing 0.9 amps, so it's equivalent to the normal charger, while the USB-C port is capable of sourcing 3 amps, so it's equivalent to the fast charger. To convert one to the other, the cost is the following. $29 to buy the 18-watt charger plus $19 to buy the USB-C cable. Here's the regular cable, here's the USB-C cable. Finally, the third option is by using the wireless charger, which is available in all recent iPhones. All of them are the low power version. Talking about wireless charging, the standard is called the Qi standard. It considers low power up to 5 watts. In that case, it should transfer energy using this range between 110 and 205 kilohertz, and medium power above 5 watts. Most chargers fall in this range here, 5 to 25 watts. And then it has a larger range to operate between 80 and 300 kilohertz. The operation is the principle is very simple. This is the primary coil, which is in the charger, and the secondary coil is here, which is inside the smartphone. It's just by induction. Here's the case of iPhone 11. This is the coil, many turns, and here's where it is installed. Next is the logic board, which is equivalent to the motherboard in a computer. In recent iPhones, it is indeed a set of two boards with components soldered on three faces. This is illustrated here. This is the lower board with components on one side, and this is the upper board with components on both sides. This is usually reserved for radio frequency devices, while here the main component is the main processor, and on this face here, the main component is the flash memory. These two boards are brought together and are soldered all the way around, so this is the final logic board. Some examples. First, for the iPhone 10, here's its location. When you open it, this is the lower board, single phase, reserved for radio frequency devices. The upper board, down phase, the A11 processor is the main device, and the upper board, up phase, the main component is the flash memory. Now for the iPhone 11 Pro. Again, the location is about the same. The lower board, again reserved for the radio frequency devices. The upper board, the down phase, the main component is the A13 processor, and the upper board, up phase, has again the flash memory as its main component. Notice that this dotted line around here aligns with the dotted line down here, and this is where the two boards are soldered together. We move now to the main processor. The most recent versions are A12 and A13, the latter for the iPhone 11 group. The processor has been designed by Apple and manufactured by TSMC for a number of years now, and the technologies used by TSMC are 7 nanometers for the A12, and then an enhanced 7 nanometer version for the A13. But what does 7 nanometer technology mean? Generally speaking, it is the size of the smallest thing that can be fabricated in that process. More objectively, at the time of planar MOS transistors, it was approximately the channel length of the smallest MOSFET that could be built in that process. Just to illustrate it, the technology node in the first integrated circuit was 10 micrometers, and that was 49 years ago. As of 2020, the technology node is 5 nanometers. To reduce electric current leakage, newer MOSFETs, typically under 30 nanometer technologies, are three-dimensional, so the criterion above no longer applies. So before, in the planar technology, the gate was just a plate over the channel, which is the region that connects source to drain. Now the gate embraces the channel. So the channel length, which is this distance here, no longer is a measurement of the technology. One very simplified way to classify a process is to consider the size of a MOSFET in a planar process would have to be to exhibit comparable parameters like transistor density and speed. This subjectivity obviously makes process comparisons more difficult. For example, the 7 nanometer process used by TSMC in the A12 processor 2018 was not truly superior to Intel's 10 nanometer process of that time. Just out of curiosity, how big is 7 nanometers? Here's the silicon crystal. It is about 0.5 nanometer on the side. So if we do the calculation, we conclude that just 13 cubes suffice to get 7 nanometers. So this is very small. Or in terms of atom layers, 53 atom layers. An actual example, a 10 nanometer transistor from Intel using the P1274 process. Here is the sketch once again. This cross-section is taking over the gate, so the channel length does not show up in this picture. It's probably around 20 nanometers, so it is more than the technology node number. Notice that these numbers are all very small, and the fin width is just 7 nanometers. So it does not define the technology node, but it's the whole construction that defines it. But if you want the technology node number to be small, these numbers have to be small as well. Talking about transistor fabrication, foundry or fab is the name given to a facility where integrated circuits and other devices are manufactured. Examples of companies with the biggest foundry capacity are Intel, TSMC, Samsung, and ST Microelectronics. The largest facility of them all is this one in Chandler, Arizona, where Intel had already 3 foundries and is finishing now the 4th foundry, which is called Fab 42, with a budget of $7 billion. This table summarizes the main parameters of the newest 3 iPhone processors, A11, A12, and A13. It was designed by Apple in all 3 years. It was fabricated by TSMC, and the technology employed by TSMC was 10 nanometers, then 7 nanometers in a process called N7, and finally an enhanced 10 nanometer version in a process called N7 Plus. Note that for 10 nanometers and 7 nanometers, deep ultraviolet lithography is used as listed down here, while for the A13, extreme ultraviolet lithography is used. TSMC reported a 17% higher transistor density and 10% faster transistors in the latter. The CPU has 2 high-performance cores and 4 low-power cores in all 3 years. The GPU had 3 cores in the A11 and 4 cores. The fastest clock is about 2.5 gigahertz. The neural engine, which is part of the main processor, had 2 cores, then 8 and 8. Then there is cache memory, and finally the transistors, which doubled in 2 years from 4.3 to 8.6 billion transistors. The speed and power consumption gains are roughly estimated something between 15 and 25% over the previous generation. We close this video by showing a short video from Intel about Fab 42. It's very interesting, and it's not every day that we have the chance of seeing a foundry while it's being built. I thank you for watching, and I invite you to come back again for video number 3.
In 2017, we announced plans to invest $7 billion into Arizona's Fab 42. Come along with me. I'm going to show you the progress and 3 cool things about one of the most advanced manufacturing plants in the world. Fab 42 is expected to create more than 10,000 jobs, 3,000 of them in high tech. Currently, it's one of the largest construction projects in the United States with almost 6,000 men and women in hard hats. Cool thing number 1, the mega factory. When completed, Fab 42 will be part of a larger Arizona network of Fabs 12, 22, and 32, all of them eventually being connected to run as one factory. To outfit Fab 42 with tools, and we're not talking screwdrivers and hammers, it typically takes 2 semi-trucks to deliver most of the Fab's 1,300 tools. A single tool typically arrives in 40 crates. So to fully outfit the factory, trucks will arrive with more than 50,000 crates. Some of these tools weigh as much as 5 tons, or about the weight of 4 mid-sized cars. Cool thing number 2, the automated superhighway, or as they call it here, ASH. Automated material handling systems like these are common in our factories. Those things you see moving on overhead monorail systems are called FOUPs, front opening unified pods. Each FOUP carries as many as 25 wafers on their journey from blank silicon discs to wafers containing up to hundreds of Intel chips. Arizona's Ash 1 and Ash 2 connect all 4 factories. End to end is a distance of 1 mile. Every hour, about 1,000 FOUPs move through each ash. This system allows Arizona to run multiple technology nodes in the same factory network, taking us away from the traditional model of a single node factory. And finally, cool thing number 3, the water treatment and reclaim facility. Every day, the 12-acre facility will treat 9.1 million gallons of factory wastewater. It will reclaim 20% back into Fab 42 for its cooling towers and scrubbers, and send the other 80% back to the city of Chandler for irrigation. The facility will decrease the amount of water we receive from Chandler and the demand on the city's treatment facilities. Intel has set a goal to restore 100% of our global water use over the next decade. And that is pretty cool. Thanks for watching. I'm Rob Kelton.